now we're going to get into a discussion of the periodic table. So this is just going to be a bit of an introduction. Later on, we're going to delve into it in more detail, especially when it comes to understanding how the elements are arranged in the periodic table. But for now, we're going to talk about how the periodic table came to be. And the first periodic table that was ever designed was by a Russian scientist by the name of Dmitry Mendeleev. And he discovered that if you write down the elements according to their increasing atomic mass, then you find that after so many elements, their properties repeat themselves. So he basically took to trying to organize these elements in such a way so that elements having the same property will be assigned to the same column. And he came up with an initial version of the periodic table, which of course has undergone some changes over the years as more elements were being discovered, and as a result we end up with our modern version of the periodic table. In any case, in any periodic table, what you'll notice is that in addition to the element symbol that is placed inside each box, there's also a number that is placed in there. And that number is called the atomic number, right? And the atomic number, by definition, is the number of protons in the atom of an element. So, for example, in the case of nitrogen, its atomic number is 7, right? 7 is, therefore, the number of protons present in an atom of nitrogen. And what you're going to learn is that each element has their own unique atomic number. And as a result, you can basically use the atomic number to identify the element. Okay, some important terms that you need to be aware of. Now, the atomic number, as I said before, is the number of protons in the atom of an element. And these protons are located in the nucleus, which is at the center of the atom. All right. In most textbooks, you'll see that they use the uppercase Z to represent the atomic number. Another number that you need to be aware of is known as the mass number. And it is basically the sum of the number of protons and neutrons in an atom of an element. And we oftentimes use the uppercase A to represent the mass number. All right. So it's very easy to determine the number of neutrons. All you have to do is subtract the atomic number from the mass number, and that gives you the number of neutrons, right? And in most textbooks, you see this kind of shorthand way of representing the symbol for an element along with its mass number and atomic number. So E would represent the symbol of the element. Z is placed down there as a subscript, which represents the atomic number, and A represents the mass number. So, for example, in this case here, Cl is chlorine, 17 would be the atomic number, and the mass number here is 35, all right? Now, we're going to learn later on that even though all elements of one type has the same atomic number, that is not necessarily true for the mass number. In fact, in the next slide, we call those atoms isotopes. Isotopes are basically elements, atoms of the same elements that have the same number of protons but different number of neutrons, right? And here's an example of a pair of chlorine isotopes. You have this isotope, which is called chlorine 35 because the mass number is 35, and this isotope of chlorine is called chlorine 37 because its mass number is 37, right? They're both chlorine, right? They're both the same element. They both behave chemically the same way. The only difference is their mass numbers, and the mass numbers are different because they have different numbers of protons. So if you're given symbols of this type, you can tell the number of protons, the number of neutrons, and the number of electrons in an atom of either isotope. So we can simply answer these questions. How many protons are there in chlorine 35? And the answer is 17. How many protons are there in chlorine 37? That is also 17. And how many neutrons are there in chlorine 37? Well, that's simple. That's simply 37 minus 17, and that gives you 20 neutrons. All right? So that's basically how we can calculate the different numbers of the different fundamental particles that are present in an atom. Okay, now, going back to the periodic table, the elements are arranged in order of increasing atomic number. The elements are arranged with um, well, they're arranging columns if they have similar chemical properties, and these columns are called groups. All right, so for example, if you look at group 8A in the periodic table, you'll see that these elements, helium, neon, argon, and so on, are present. And what you'll find is that these elements have very similar properties, and that is true pretty much throughout the periodic table. What you'll find is that elements belonging to the same column will basically behave chemically the same way. Now, these particular elements in group 8A, they are known as the noble gases. In some textbooks, they are called the inert gases, and they are known as such because they are very unreactive. In fact, helium and neon are not known to react with any particular other elements, and the others, they will react, but you have to employ some special conditions in order to facilitate those reactions. Okay, the elements in their natural states, most substances around us are mixtures or compounds, right? Now, there are certain elements that are actually found in nature in the pure form. These are called the noble metals, such as gold, silver, and platinum. All right. And then we have these elements, which are also found in the pure form, so to speak, helium, neon, argon. In other words, they're not combined chemically with anything else. All right. And air, of course, the air we breathe is composed mainly of nitrogen and oxygen gases. There are some other gases, but those are the two main gases. And in terms of what they look like, nitrogen and oxygen, their molecules are actually diatomic, which means that each atom exists as two atoms combined with each other. So therefore, the symbol that we use to represent them is N2 for nitrogen and O2 for oxygen. So those are not the only elements that exist as diatomic molecules, all right? But of course, let me go into the definition of diatomic molecules. These are molecules that contain exactly two atoms of the same or different elements. And these are the elements that exist as diatomic molecules. These are the 7 elements that exist as 2 atoms per molecule. You need to memorize these because this is important, especially when you're given a question where these elements are given, information is given about these elements, for example, participating in a reaction and so on. Okay, so make sure that you memorize these 7 elements. The last 4 on this list should be relatively easy to remember because these are group 7 elements, but then you have these 3, oxygen, nitrogen, and hydrogen, which you need to remember as well. All right? Just some general information about these elements. What you'll find is that hydrogen and nitrogen, monatomic atoms, will not be found in nature. Instead, you'll find H2 and N2, and that is true also for the other diatomic molecules. Hydrogen gas can be found in volcanoes and also can be prepared in a lab. In both cases, it exists again as the diatomic form. Air is about 21% oxygen by volume, and oxygen can also be prepared in a lab, and oxygen also exists as a diatomic molecule, right? Okay, water has a formula, as we all know, as H2O. It does not contain any free hydrogen, does not contain any free oxygen in the diatomic form. The H2 part of the molecule means that for every molecule of water, there are 2 hydrogen atoms and 1 atom of oxygen present, all right? So just to understand the distinction between the separate elements and that exist in nature and how they exist in water, this represents the hydrogen molecule, it's diatomic. This represents the oxygen molecule, which is also diatomic, but this represents the molecule of water. All right, so it's very important that you understand the difference between the free elements that exist as diatomic molecules and when they combine to form a different substance, which is a new molecule, which is water. All right, okay, so we're going to stop here, and then the next video we'll deal with further discussions of compounds.